So we have electrical quantities such as current, which is a rate of flow of the charges, voltage, it's work done or energy transferred by a unit charge. Now the third quantity is resistance. Resistance is a property of a material to oppose the motion of the charges. So when the material opposes the motion of the charges, we call that property as a resistance. So property of an object to oppose the motion of a charges through the structure, we call this as a resistance. And if you want to find the resistance by using the electrical quantities, so resistance is also a ratio between voltage and current. If we divide the voltage across the component and the current which is passing through it, we will get the value resistance, and the unit of the resistance is ohm, or you can also write or use omega as a symbol. So resistance not only depends on the dimension of the material, it also depends on the type of the material as well as the temperature. So many factors collectively will affect the resistance. The first one, the factors which can affect the resistance. The first one is length. How a length can affect a resistance. For example, if we have two sets of wire, one is a short wire, like example 1 meter long, another one is 3 meter long. Which one you expect to have a high resistance? A wire of length 1 meter or a wire of length 3 meters? So longer wire have high resistance than shorter wires, because here the charges have to pass through a greater length, so they will have more collision with the lattice of the metal, because the structure of a metal, it has a lattice of a positive ion and the free delocalized electrons. So when the charges have to pass through a longer wire, like a greater length, they will have more collision, so the number of the charges which will flow out, that will change. Say 5 charges enter the wire, but right now 4 are able to move out. So means only one is stopped. But here 5 charges when entered, they have multiple collisions. So as a result, maybe 2 charges are able to move out. So it will have a high resistance because it oppose greater number of the charges to flow through it. So we can say resistance is directly proportional to length of the wire. The longer the wire, the higher the resistance. So the first factor which affects the resistance is a length. Then we have the second factor. The second factor which can affect the resistance is the area, the cross-sectional area. So if we have two wires which are having same length but different cross-sectional areas made up of same material, which sample you think will have a high resistance, A or B? Thin wire or a thick wire? So when we compare, because in a thin wire, the charges have narrow space to move, whereas thick wires, the charges have large space to move. So resistance is inversely proportional to cross-sectional area. Thinner wires have high resistance than thicker wires. So here what will happen, because when the charges are moving, there is a like a small space for the charges to flow. But in a large cross-sectional area, they have large space to flow. So if we reduce the area, that will increase the resistance of the wire. So thin wires have high resistance than thick wires. And if you want to find the area of the cross section of the wire, area is pi r square, or you can also use pi d square by 4. So what it relate, like example, if we double the diameter or the radius, what will happen to cross-sectional area? It will increase by 4 because it vary with the square of radius and diameter. If you triple the radius or a diameter, then the area will increase by 9. If a radius is 4 times the original value, the area will increase by 16. So if you double, it will increase always with a square. So if it is 4 times, it will be 16. If the radius or diameter changes by 5 times, then the area will change by 25. So it always vary with a square. Because the formula for the cross-sectional area is 4, area of a cross-section of a wire is pi r square. Pi is constant, pi is not changing. So what will happen? If radius is double, radius is 2 times, square of 2 is what? It is 4. So area will be 4 times. If a radius is 3 times, if you multiply by 3, what will happen to area? 3 square is 9. So this will become 9 times. If area is 4 times, if a radius is 4 times, the area will increase by 16. So always vary with a square. So long wires and thin wires have high resistance than short and thick wires. That is why when you see a filament of a bulb or a heater, you will find it is coiled and it is very thin. So why it is coiled? Because when it is coiled, it will have a greater length in the same distance. And why it is thin? Because it will have a high resistance. So as a result of both of these, it will have a high resistance. Greater the resistance, greater the energy change, like in the form of heat. So that's why the heating coil or the filament bulbs, the filament of the bulb is always having a very thin wire with a small, which is having a small cross-sectional area as well as coiled, so it will have a longer length. So if we combine these two factors, we know resistance is directly proportional to length and the resistance is inversely proportional to cross-sectional area. So if we combine, we can say resistance is proportional to L by A. The ratio, because if we combine these two, this is numerator, length, and area in denominator. So we combine resistance proportion to ratio between length and area. Like if this ratio changes, ratio of a length and area changes, the resistance will also change. When we replace the proportionality sign, we always replace with a equal to and a constant. So this expression will turn into equation. So R is equals to rho L by A, where R is a resistance, L is a length, A is the cross-sectional area of the wire. And what about rho? Rho is called resistivity. It is not density. It is called resistivity. It's a constant for every material at a specific temperature. Like a copper wire at 25 degrees centigrade will have a fixed value of resistivity. Same thing, aluminum wire at 25 degrees centigrade, it will have a fixed value of resistivity. So resistivity is same like density, but it's in terms of electricity. Like how much resistance for a wire having a length of 1 meter and area 1 meter square, that is called resistivity. Like, say we have a wire which is having a total length of L and the cross-sectional area is A and the total resistance is R. What is the concept of the resistivity? If we take a wire, a section of a wire which is having a length of 1 meter and having an area of 1 meter square, so resistance of this part is called resistivity. And every material is having a unique value of a resistivity. So using a resistivity, we can also identify the type of the material. Because like the resistivity of a copper will be different from resistivity of the iron. But the condition is that it must be at a fixed temperature because the resistivity changes with the temperature. As the temperature changes, the resistivity will also change. Resistivity is a resistance of a wire which is having an area of 1 meter square and a length of 1 meter. Like the resistance of a section of a wire of an area 1 meter square and a length 1 meter, that section resistance is called resistivity. So you may have a wire which is having like total resistance of 100 ohm. Maybe the total length is 2 meter and the total area is like 5 meters square. But when you take out the section of this wire, of a length 1 meter and the area 1 meter square, the resistance of this section is what we call that as a resistivity. So every material is having a unique resistivity at a specific temperature. Is it clear, the concept of resistivity? So if we have two wires, they have different lengths and different cross-sectional areas, so we can compare them if they're made up of same material. Like let's take two copper wires are there. Length is L1 and area is A1 and resistance is R1. Another copper wire, which is having an area of A2, resistance of R2 and the length L2. So if I write the equation to relate resistance, area and length, so we have the formula that R is equals to rho L by A. Because the two I mentioned both are made up of copper, so they will have the same resistivity irrespective of their length and area. So I can say R1 A1 over L1 is equals to rho. For this one, the resistance is R2, so its resistivity is rho, length is L2 and area is A2. So if we write rho here, resistivity will be equals to R2 A2 over L2. Because these two wires are made up of same material, so it will have the same resistivity. So I can compare these two equations. I can say R1 A1 over L1 equals to R2 A2 over L2. So this is the formula which can be used to compare the resistance, area and length of two wires which are made up of same material. If the two wires are made up of different material, then I cannot use this formula. The condition is that because the two wires are made up of same material, so we can compare the resistivity of the first wire with the second one. Is it clear, this one? Any doubt in this part about the resistivity? Okay. So the factors which are affecting the resistance, the first one was a length, the second one is a cross-sectional area. The third one is a temperature. Temperature can also affect the resistance. How a temperature can also affect the resistance, but it depends on the type of material as well. We may have a conductor. So in a conductor, the resistance increases with the temperature. Why the resistance increases with the temperature? Say in a metal, we have a lattice of a positive ion and the delocalized electrons. When we increase the temperature, the lattice vibration increases. Like this positive ion lattice, it will move at a higher speed. So as a result, when the lattice vibration increase, the particles which are flowing find it difficult to move. So as they find it difficult to move, maybe the 5 charges enter, but out of 5, only 2 are able to move out. So when for a conductors, for metals, when we increase the temperature or when the metal temperature increases, it increases the lattice vibration. The increase in the lattice vibration increases the collision between the motion of the movement of the electrons, like the electrons and the lattice. As a result, the electron like the speed decreases or the drift speed decreases. That's why they're not able to flow out. So the resistance increases. We can also relate by a transport equation. According to a transport equation, I is equals to NAQV. Here, N is not changing because it is fixed. A is not changing, the cross-sectional area, Q is not changing. All of them are constants. What happens as we increase the temperature, the drift speed decreases. As the drift speed decreases, the current will also decrease. And what is the relation between the current and the resistance? If the current is decreasing, the resistance will increase. So for a conductor's, how drift speed is decreasing? Because say this is an electron, it's moving. As the temperature increase, it moves more random. So as more random motion, less displacement. Because more random motion is there. If less random motion, greater displacement. So the drift speed, this electron is colliding with the lattice, it's not able to cover more distance in the same time interval. So the drift speed decreases. As it drifts, so remember always increase in temperature, always reduce the drift speed. So as the drift speed decreases, the current will also decrease, and decrease in the current means the resistance of the material has increased. So for the conductors, increasing a temperature increases the resistance. Is it clear, this concept? Anyone having a doubt or a question about this? Okay. The next is, because we have another type of a material which is semiconductor. What happen in case of a semiconductors? What is the effect of temperature on semiconductors such as light dependent resistor or thermistor specifically? So the structure of a semiconductor is a bit different from the metal. The structure of a semiconductor, it consists of a giant covalent structure. There's a giant covalent structure. So what will happen? You can, when we increase the temperature, we observe the resistance of a semiconductor decreases. But why it happened like this? So because yesterday we did, because of the heat or the light energy, the electrons start to move out. Because there's a heat or the light, the bonded electrons start to move out, so the number of electron increase. We can also explain in terms of the transport equation. According to a transport equation, we have I is equals to N A Q V. A is not changing because it's a cross-sectional area, and Q is not changing. When we increase the temperature, the number of the charge carrier increases. More charge carriers are there. What happened to a drift speed? Will it increase or decrease? When you increase the temperature, the random motion, will it increase or decrease? So the random motion, when you increase the temperature, the random motion increases, so drift velocity decreases. So what happened when the temperature is increased? When the temperature is increased, the number of the charge carrier will increase and the drift velocity will decrease. But increase in the number of the charge carrier is much higher as compared to a decrease in the drift velocity. Drift velocity is decreasing, but increase in the number of the charge carrier is higher than the decrease in the drift velocity. So overall, what will happen? The current will increase. As the current will increase, the relation between the current and resistance inverse. So if the current is increasing, the resistance is decreasing. So in a semiconductors, what happened? When we increase the temperature, it increases the number of the charge carriers as well as it decreases the drift speed. Two things happen. One is increasing, another one is decreasing. But the increase in the number of the charge carrier is much higher than decrease in the drift speed. Why the drift speed become random whenever, like, drift speed is when when we increase the temperature, the charges move more randomly. When they move more randomly, when there's a random motion, what will happen? The displacement decreases. That is why, like example, in case of a dust storm here, like if you have a dust storm, what you will find that when it is too windy, you will find that it will take much longer time for the dust to settle down. Why it is this? Because when it is too windy, the dust particles are moving more random. So when they have greater random motion, they will take longer time to reach the ground. But when it is very low wind speed, as a result, there is a random motion, but less random motion, and eventually the dust will settle down. So the drift speed is a displacement over time. If the if we talk about, like, if it is having a shorter displacement, or if we have the constant displacement, if it take a short time, it means it has a higher drift velocity. If it is taking if it is taking a longer time, means it is having a lower drift speed. So because when high temperature, the particles take much longer time to move out from the wire or from the material. So it means that the time is longer. So the drift speed is smaller. So greater random motion, lower drift speed. Higher random motion, lower random motion, higher drift speed. Is it clear? The semiconductors and the effect of temperature? Yeah, particles move faster at high speed, but they're not moving in a straight line. The particles move very fast, but they're changing the direction many times, which result in a lower displacement. If the particle is moving slower, less time, like what will happen? Less number of time it will change the direction, so more displacement. So even though the speed is higher, but the displacement is shorter. So for a semiconductors, when you increase the temperature, the resistance will decrease. But for conductors, when you increase the temperature, the resistance will also increase. And for semiconductors, there is no effect of temperature. For insulator, there is no effect of temperature. If you increase or decrease temperature, it won't affect the resistance. Theoretically, practically, there will be a temperature at which even a glass, even it's an insulator, but at a specific temperature, it start to conduct electricity. Then we have electrical power. This was about the resistance. Electrical power, it is rate of work done or rate of energy transfer. So how much work is done in a unit time, or how much energy, electrical energy transfer, we call that as a power. So we have the formula for electrical power, or any, so power is work divided by time, or power is energy divided by time. But here we use, in electricity, we use the quantities such as voltage, resistance, and current. So we should rearrange this formula and write in terms of voltage, resistance, and current. So we have the formula that the voltage is energy divided by charge. That's a formula for voltage. So if I need energy, so energy will be voltage into charge. So I can substitute, in place of energy, I can substitute voltage into charge, and T is the time. What is charge divided by time? Which physical quantity we get when the charge is divided by time? So charge, rate of flow of the charges, what we call that? The flow of the charges in a unit time, we call that as electrical current. So we can say this is I. So if we simplify this formula, we got P is equals to V I. That the power is the product of voltage and current. And there are other formulas as well. We can relate by, like, V is equals to IR. We have V is equals to IR. So in place of V, if I write IR, so the power will become P is equals to I square R. This is one of the formula we can use. If we have the current and resistance, we can use this formula. Or we can also use I is equals to V over R. So in place of I, if I substitute V over R, so this will become P is equals to V square divided by R. So that's another formula. So different formulas of the power, like three different formulas of the power, depending on the question. If we have voltage and current, we can use the first one. If we have current and resistance, we can use I square R. And if we have voltage and resistance, we can use the third formula. And the unit of the power is watts. Is it clear? This one? Yeah, power dissipation, we only use this formula. Power dissipation or power loss in the form of heat, because the power loss depends on the current. Higher the current, greater the heating effect, more energy will be lost, or higher the resistance, greater the energy loss in the form of heat. So power loss is always calculated by this formula. But power of the component can be calculated by any three of them. So third, this formula I square R is also known as the power loss formula. Then we have resistance in the circuits, or resistance in a circuit we'll do next session, as the small derivation is also there. You should be able to derive a formula. You have learned that formula about the resistance in the circuit, the derivation, but this time derivation is also there. Any question or doubt related to the session today?